So let's say that we need to prepare the buffer solution with the pH 7.45. And we also know that the solution we need to prepare is from dibasic, monobasic and dibasic phosphate. Actually, this is what we'll prepare also in the lab. And also we know Ka. So Ka is 6.2 times 10 in power minus 8, which means that we can calculate pKa just taking the negative log of this number. So negative log of this number is pKa. And if you calculate that, it's going to be 7.21. Okay. So now what we know is that we know pH because this is what we need to prepare, which is 7.45, right? Okay, so we'll plug it in over here. So which is 7.45. Also, we calculated pKa over here. Okay. And now we need to calculate the ratio of HPO4 to minus over H2PO4. All right. Now let's just see how to do it. Okay. So after everything, so say we need to calculate from here, right? So from here, it's going to be 0.25. So how did we get the 0.25? It's 7.45 minus 7.21. It gives us 0.24. Okay. And then from here, we can find the ratio. We can find the ratio of HPO4 to minus and H2PO4 minus. So it gives us 10 in power 0.24, which is 1.7. So the ratio is 1.7. So we know that to prepare this phosphate buffer solution with pH 7.45, we need to dissolve the sodium hydrogen phosphate and sodium hydrogen phosphate in a mole ratio 1.7 to 1. So it means that this one is 1.7 times higher than this one. Okay. For example, we can take 1.7 moles of Na2HPO4 and 1 mole of NaH2PO4, and it's enough in enough water to make just 1 liter of solution. So here you will have in your quiz, for example, you will be given, for example, let's just say if you're given, so you say, let's just continue from here. And let's say the concentration of H2PO4 is, let me think. Yeah, so you know what? You can have an example like that way. So you need to find the pH. Say you don't know the pH. Let's just go back. Forget about the pH, okay? Let's just say you don't know this pH. All right, so you know this. Also, you know the concentration of this one is going to be 0.01. And concentration of this one, which is going to be 0.001. M and M, okay? So these are concentrations for conjugate base and conjugate acid. So how to find the pH? So you just plug 7.1 here and all these concentrations. So we'll have pH is going to be 7.21 plus log of 0.01 or 0.001. Okay, so then it's gonna be 7. Can somebody calculate it? So what's gonna be this number? Okay, so what is the 0.01 divided by 0.001?
10.
10.
10.
So then it means that we have log of 10. So what's gonna be the number for this?
1.
Yes, it's gonna be 1,
1,
right? Yeah, so then it's plus 1. So it means that the pH is gonna be 8.21. Okay?
Doctor, I
Yeah.
want to ask you, we must know the equal of log. We must know logarithm, log 1, log 2, or
Okay.
you will give us.
Okay, listen. You must know logarithm of 10. You must know logarithm of 10. You must know for example,
Yes,
logarithm of
yes, Doctor.
100.
It is similar.
Yes. So you must know these kind of things. But of course, I don't know, for example, logarithm of 2. I really don't know that. I know logarithm of 1. You must know also what is logarithm of 1.
0.
Exactly, it's 0. Right, it's 0. You must know this one, but you cannot know logarithm of 3.
You will give us.
No. I'll give you the number like this one, for example, like this one, or for example, logarithm of 0.01. You must know also this one. Do you know why? So can you write in a different way this one here?
-3.
No, it's not -3. It's 0.01. It's not -3.
10 in power -2.
Doctor, it will be
it's gonna be
0.1.
it's gonna be 10 in power -2, and somebody said that, and then it's just -2. Okay.
Yes.
So this kind of thing you must know. I mean, you don't need a calculator for this. Okay. So this is a base of 10, right? We don't write it, but it's always like base of 10. So this kind of thing you must know, but of course you cannot know. I don't know myself what is the logarithm from here if it is like 10. I know what is the logarithm, for example, with base 3 out of 9, right? That's simple, it's 2. Okay, this kind of thing you must know as well, but I mean, this one, nobody, I mean, I don't know myself. You need a calculator for this. All right? All right, so now, is it clear all this stuff about buffer and pH? All right, so then we need to consider different subject, different material. Now we need to move to colligative properties, okay? I uploaded the lecture, but let's just discuss like about colligative properties. It's over here. All right, so this is quite important to understand and know about this, about osmosis and dialysis and colligative properties. before we go to electrolytes in body fluids, right? So we have electrolytes. We have heard about that, you know, somebody was given some electrolytes because there was lack of electrolytes for in body fluids. So then these electrolytes are measured using units like equivalents and milliequivalents. And I'll explain what does it mean. But before that, why we are doing this, I just want to explain that one, okay? Why it's important? Because we have already know concentration, right? But why do we need to know now milliequivalents and equivalents? So say you have equation like NaCl plus KNO3. Can you tell me what's going to be the result here? Can somebody tell me that?
KCl
Okay. Then
NaNO3.
plus NaNO3. Okay, now what I want you to do is that I want you to tell me what's going to be the ionic equation here. If you break down all these things in ions, what's going to be the equation?
Na plus Cl, Na plus Cl minus
Then
Ca plus and OC minus
right? Okay, now what's going to be the net ionic equation here? Can somebody
No,
tell me what's
I
going to
think
be
it's
the,
right.
huh?
I think it's wrong.
Yeah, so there's no net ionic equation, right? Because all these are canceled.
Because there are not
So what is happening here is that when you mix these two, you never know which one you have. Like you have basically here all the mixture. You have KCl, you have KNO3, you have NaCl, and you have NaNO3. You will have all these mixtures because the reaction between these two will never happen like this one. Okay, so all of these are spectator ions, or you will have just a mixture of all of these. Sometimes you will have these, sometimes these, all of them, okay? All the time. So now it's really difficult to understand what is the concentration of KCl or NaCl or NaOH or NaNO3 or KNO3 because you have all of these together. Okay, so just they exchange ions all the time at equilibrium, some kind of equilibrium, but all the time they exchange ions. You have all of them at the same time, basically, right? So in this case, it's really difficult to understand what is the concentration. But in body fluids, as you guys know, we have K plus, we have Na plus, we have Cl minus, right? We have all these ions in there. So how to understand how much do we have all these ions in there? Okay, so concentration doesn't work because, as I said, we have like, you know, all of them like together, right? So because of this, there is another parameter used, which is equivalent and gram equivalent. So simply, what is equivalent is it's equal to the number of ions that carry 1 mole of charge. So what does it mean? For example, if we have all this mixture of these ions, right? So then say if we know that we have 1 mole of sodium ion, we don't know how much we have sodium chloride or sodium nitrate, but we know that we have sodium, right, in there. So as a sodium ion, for example, if I go back, we definitely know that we have this sodium, right? So for example, here and here. Okay, but we don't know exactly what is NaCl, NaNO3, but we can calculate what's going to be the overall number of Na plus. So it means that we can calculate how many moles of Na plus we have. Okay, so because of that, there is a parameter called equivalent, which says that it just equal to the number of ions that carry 1 mole of charge. Okay, so say if we have 1 mole of sodium, it means that we have 1 equivalent of sodium ions. Okay, so to make it more simple and understandable, there is a parameter, another one called gram equivalent. For example, if you take 1 mole of sodium ions, right, which is say in the blood, just imagine, there is not that much, but just for simplicity, or in water in somewhere. So if we take this 1 mole of sodium ions and we measure the mass of these sodium ions, that's going to be the gram equivalent of sodium ions. Okay, so simply if we want to find what is the 1 gram equivalent of ion, we just need to take molar mass and divide it by charge on the ion. For example, for the sodium, which we are talking about sodium, gram equivalent and molar mass are the same because the charge of sodium is just 1, right? But let's say if you take the calcium, so calcium has charge, which is 2 plus. Okay, so you need to find first what is the molar mass of calcium, and then you need to find what is 1 gram equivalent of ions of sodium, calcium. Okay, so to find 1 gram equivalent of ion of calcium, you need to take molar mass of calcium in grams and divide it by charge on ion. Can somebody find the molar mass of calcium? Okay, hello, somebody can find the molar mass of calcium, calcium, just calcium.
Doctor, I think 14.
No, it cannot be 14. Molar mass 14 is for nitrogen, 14. 40, you say 40 or 14?
40.
Yeah, 40. So that's the molar mass of calcium. So if you want to calculate the 1 gram equivalent, so you just need to divide 40 by 2 because we have charge 2, right? So this is what's going to be the 1 gram equivalent of calcium. So it says over here, if the ions has charge +1 or -1, then 1 gram equivalent of the ion is simply the molar mass of the ion in grams, okay? So very many times we are using milli equivalents instead of equivalents because it's more convenient, because actually the ions, amount of ions are very small in blood. It's not that much to measure it in equivalent. So this is why it just measured it in milli equivalents, okay? this is a real amount of sodium, calcium, potassium, magnesium, concentration of milliequivalents per liter. Okay, in blood plasma, it's a real case in blood plasma, and you can see that a little bit the cations are higher in concentration, taking in milliequivalents per liter than anion. So this is anion, this is cation, right? So plus is cation, and it says cation. It should be cation. It's not cation. It should be like this one, opposite. This is anion. So why it's like that? Because the table, so I don't, the difference called the anion gap is made up by the presence of negatively charged proteins and the anions of organic acid. So there is some additionally proteins which might have negative charge, and this balances the gap between positive and negative charges. Okay, let's just look at the example. It says that the normal concentration of calcium 2+, you can read here at the very top. So the normal concentration of calcium 2+ is 5 milliequivalent per liter in blood. So what we have in blood is 5 milliequivalent per liter. Now let's just see how many milligrams of calcium 2+ are in 1 liter of blood. Okay, let's just see in real case, like in milligrams, how much is that? So what we have that is that we are given a volume and the concentration in milliequivalents per liter, and we need to find amount of in milligrams. Thus, we need to calculate the gram equivalent for calcium 2+, and then use concentration as a conversion factor between volume and mass, as indicated in the following flow diagram. Okay, let's look like that way. So we know the volume of blood, right? So it says in 1 liter. Okay, this one is here, right? Okay, so then we need to find the milligrams of calcium 2+, right? Okay, so we also know that in terms of milliequivalents per liter, this is 5 milliequivalents per liter, right? It's over here. All right, and then we need to find the grams, milligrams. Okay, so how to do it? So we have 1 liter of blood, right? And we have milliequivalents per liter. Okay, and also what we need to know is milliequivalent, so 1 gram equivalent basically of calcium ions. And how to find this is that 40 divided by 2, right? As you said, like this is molar mass, this is charge. So this gonna be, the number is gonna be here. This is gram equivalent of calcium, this one. Okay, so we know milli equivalent, so we know gram equivalent. Okay, so then we can find that it's going to be 100 milligram of calcium 2+ in 1 liter of blood. Okay. All right, so now let's just move to colligative properties. What are colligative properties? You might sometimes meet this kind of number. So to understand is that it means that the vapor pressure is lower for a solution than for a pure solvent. I'll explain what does it mean. Let's just go through this. Then boiling point is higher for a solution than for pure solvent. Freezing point is lower for a solution than for a pure solvent. And osmosis occurs when a solution is separated from a pure solvent by semi-permeable membrane, okay? So, yeah, so all these are considered as colligative properties. Now let's just go step by step and understand what does it mean. Let's just talk about vapor pressure above the solution. Okay. You can look at the picture here. You can see that this is a pure solvent. For example, this is water. And we have only water molecules, right? Some of these molecules are in as a water, right? But some of the molecules are like a vapor, right? Because water vaporizes, right? So some of them is just like a vapor. And here above the solution, we have vapor and it has particular pressure over here, which is, it doesn't matter what is the unit, but say it's 3, right? So it says 3. Okay, so then we have another case. So we have solution with a non-volatile solute. Say this is KCl in a solution. Okay, so now we have molecules of water and we have molecules of KCl, right? So now you can see that we have less vapor molecules over the solution, right? So why it's happening? So why it's happening is the reason is that so KCl molecules of KCl can occupy some space on the surface as well, right? Or inside as well, right? So if the molecule of water evaporates, there must be another molecule coming, for example, this one. But to come to this point, it's very difficult for this molecule because there is a KCl in front of it. So to escape for this molecule is really difficult because of KCl. The same thing, to escape, for example, for this molecule is also difficult because in front there is KCl and so on. So because of that, escaping in vapor for water molecules is complicated. And the pressure of the solution water pressure becomes lower, okay? Did you guys get the point or not?
Yes, thank you.
All right, so I'll skip this one because you can just read it yourself. Okay, now, because of this, what I explained, boiling point of solution is higher than boiling point of pure solvent. And this is used for in case of sterilization. So when somebody wants to sterilize something, in order to elevate the temperature of vapor, they make some kind of mixture of salt and water, and then the boiling point becomes higher. So what does it mean is that you need to heat up solution more, okay, than water to boil it. So if you can boil water, pure water at 100 degrees Celsius, then you need to have 101 degree Celsius if you want to boil solution which contains KCl, for example. Okay. So
you mean you need more temperature?
Yes, exactly. You need more temperature to boil the solution. And because of that, the vapor which is produced during this boiling is hotter than the vapor of pure solvent. Do you guys understand? So because of this point, it is used in a sterilization process. For example, if you want to create some kind of very, very hot environment in there, inside of the chamber, you can have some kind of solution, then it can be vaporized, giving the high temperature for vapor. And it's good for sterilization because say some bacteria might not be dying at 100 degree, but they will die at 130 degree. Okay, so it's good in that sense. So that is used for sterilization. So see here it says boiling point of H2O, it's over here, and it's like 100 degree, but boiling point of H2O plus NaCl is over here. It's 101 degree. Okay. And the same thing actually for freezing. Actually, the just as solution have lower vapor pressure and consequently higher boiling points, then pure solvents, they also have lower freezing points. Okay. So for each mole of non-volatile solute particles, the freezing point of 1 kilo of water is lowered by 1.83 degree. Okay. Oh, I have less than 1 minute, but please come back once this is off, this Zoom, okay? So we'll continue some more. By the way, this was used to have some kind of ice in the past because, yeah, so the freezing point depression has much the same cause as vapor pressure lowering. Solid molecules are dispersed between solvent molecules throughout the solution, thereby making it more difficult for solvent molecules to come together and organize into ordered crystals. So it's like, you know, complicates to make a freezing of the solution. Okay, so next, what we need to go through is osmosis and osmotic pressure. So what is osmosis? The osmosis is the passage of solvent